So in the previous lessons, we looked at light and we looked at that it has both wave and particle property. And you're wondering, why did we study light? And it's because we want to study electrons. And why do you want to study electrons? It's because if the electrons are very far away from the nucleus, it can come off and react or explode when it reacts. So the electrons tell you how elements or substances react. So the main question is, where is the electron? So according to Bohr's model, the electrons are in energy levels, which we still do believe to this day, but they are not orbiting. And the problem is we don't know exactly where they are. So here is an example of something called X-ray diffraction. So what you do is you give an X-ray beam onto a crystal if you want to know how the atoms within that solid is arranged. For example, if it's a DNA molecule, you shine an X-ray beam and you can diffract that X-ray beam, and you can tell that there's a helical structure in the DNA as given by the diffracted rays. You can do the same thing with an electron if you wanted to know its position. You might think that. So you hit the electron with an X-ray, and hopefully that light gets diffracted and you get the position of the electron. Well, no, that won't work, because if you hit that electron with an X-ray, that electron will come right off. So you cannot know where it is based on its diffracted rays. So the problem is, where is it? We don't know. Okay, if you've ever heard of Schrodinger's cat, it's a cat in a box, and it's inside the box is a vial that when opened will kill the cat. So you can't so you don't know, so the box is closed and you don't know whether the cat is dead or alive. If you open the box, there's a lever that will hit this vial and open the flask and kill the cat. So you cannot open the box. Okay, which means you can never tell if the cat is dead or alive. Same thing with an electron. You can never tell where the position is if you hit it with an X-ray beam. Therefore, we cannot analyze it physically. Erwin Schrodinger came up with an idea where he will use mathematics or calculus to find out where it is approximately. So this is what he came up with. He knows that hydrogen has one proton. He also knows it has one electron. So he plugged it into his equation and he found, oh, that's where the electron is. And he plugged it in again, oh, the electron's over here. And remember, this is a three-dimensional system. We have an X, Y, Z coordinate system. He plugged it in again, and he keeps plugging in where the electron might be in his those are dots, in his machine, or in his computer, or in his calculation. Okay, plugged it into his formula, and he found that where the dots are the most likely position of the electron using his formula. Okay, remember, each dot is the same electron. Sometimes the electron is here mathematically, sometimes the electron is here, so just one electron. So finally, he came up with a density map, which is the probable location of the electron. So here they are, those are all dots. And he said, oh, that one electron might be there. Okay, if that one's filled up, actually you can fit two electrons in that area in space, or volume in space. If that one's filled up, two electron there, then you have to put it into the next energy level, somewhere in there. If that's filled up, then you can fill it up in the third energy level, somewhere in there. Okay, so that's how we know the approximately where the electrons are. We call this the quantum mechanical model of the atom. It does look at energy levels because energy is still quantized. And we can see here that the electron can be in that dot somewhere in there. And you keep filling up the atom as it gets more and more electrons. Okay, so this is Schrodinger's equation. When he plugs it in there, he knows the approximate location of the electron. It describes both the energy and behavior. of the electron. It has both its wave and particle behavior. Okay, it's proportional to the probability of finding an electron. So it's just a probability. It's probably there most of the time. Okay, it leads to something we call quantum mechanics. We cannot pinpoint an electron in an atom, but we can define or we can guess the area in space where the electron is. This is called a density map. This is a three-dimensional area in space called orbitals. Okay, so an orbital in this case is not like orbits. They are areas in space. These are all orbitals. Okay, if the area in space looks like a sphere, it looks like this. The electron is in there somewhere. If it looks like these lobes, like they look like dumbbells, these three are called p orbitals. One in there, or maybe both in there, or one here and one here. It can be in there somewhere. Okay, or if not in there, they can be in the d orbitals. Okay, and there are 5 different d orbitals, so 5 different locations, possible locations of the electron. So if I say, oh, the electron is in the s orbital, it's somewhere in this sphere. If I say in the p orbital, this is the z-axis, I can say this is called pz orbital. I can say the electron can be on top or the bottom of the nucleus. If I say in the p, this is the x, px, it can be to the right or to the left, or py, it can be to the front or the back of the nucleus. Okay, and the d is somewhere in there. Okay, now if you're filling the atom, you fill them 2 electrons at a time. This is the first energy level, the s orbital. You can fit 2 in there, 1, 2, and each arrow is an electron. If that's filled up, you can fill up the second energy level of electrons. 1 electron, 2 electron. If that's filled up, since the second energy level has more room, you can fill up the p orbitals, 2 in there somewhere. Then you can fill up, that's a pz, the py, fill that up, and then the px. Okay, and then if that's all filled up, you can go to the third energy level sphere. And the electron can be in there somewhere. Okay, so more on that in the next lesson.